Okay.
All right, fantastic. Yeah, good evening, everyone. So we're going to talk about clustering this afternoon, or this evening now. Okay. So what's on the agenda? We're going to talk about clustering, what DR packages are involved. I'm going to go through the data set I'm using, some of the code, what's PCA, and some of the plotting techniques. That should pretty much take up a good hour. All right, clustering. So typically clustering is, it's as the word would convey, it's meant to group objects together that are similar. Typically, you would use, from a statistical perspective, you'd use a distance method to actually figure out what the closest objects are or the furthest objects, and then we'll go into what the differences are in between. And it is used in many fields. Typically, we're starting to seeing it in machine learning, in data mining, pattern recognition, image analysis, genomics, which is my side of that's typically I do a lot of genomics information and querying, so that's typically what I look at. And then system biology. So that's very used considerably in the field from a stats perspective. Machine learning typically regards, we look at it as more as a unsupervised learning. We'll get into what that means a little later on in the presentation. But typically it's when you're looking at, creating a test data set or a data frame, and then leveraging what you learn from that test data frame for your larger data frame. Also quite used in big data also. If you're involved in any big data algorithms, you typically try to use a smaller data set and then try to use a bigger one later on to be able to get, because of the time constraints that you may run into. Clustering. So one of the things you kind of look at when you're actually doing clustering, typically you'll have a data set and it has labels on it. What you're trying to find out is a little golden nugget of information. Most people know what their data is about. When you're looking at a data set, what you're trying to find out is what you don't know. And that's the key. Is actually trying to find, everything you don't know about your data. Yes, when you look at, typical, data set, you'll probably know, well, there are some certain clusters in this data, and you'll probably know what those clusters are. What you're trying to find is what you don't know, and that's the difference. Just clustering for clustering has no relevance besides knowing, you'll put together, these groups of associated items, but you want to know what you didn't see behind those associated items. That's typical, the approach. So when you're clustering, you're asking the algorithms to do the labeling for you and to point out these particular nuggets that you haven't seen within your data. So let's go next. Application part. So as I was saying, and this is a really small subset, so when you're looking at segmenting customers, you're looking at, on the clinical side, treatments and the impact of treatments, and looking at, what those particular associations within your data really convey. When you get into larger data sets, that's when, clustering really pays off, because it's hard to look at a full data set. And you'll see tonight I'm using a fairly small study that I worked on a few years back. But when you have a really large registry study with, hundreds and thousands of patients, that's when clustering kind of comes into play, and you can see better results from your, or like I say, you'll end up finding out much more about your data than you actually knew about it using clustering. And typically when, you're doing these registry studies, a lot of it, you're trying to get some of the biomarker information that can help associate in terms of treatment, in terms of being able to look at, the regimen that the subject is on, and seeing what the impact is. And these are clustering techniques that enable us to identify those particular attributes of a study. So as I was talking in clustering, unable examples, basically, what we're trying to infer is relationships within your data. So that's the key. So having the labels on your variables is all fine and good, but the relationships that the algorithms are able to pull out, that actually provides the insight into your analysis. Okay? Now we have supervised and unsupervised. Typically, when we look at predictive analysis and analytics, we're looking at typically, unsupervised approach. So clustering is typically a unsupervised classification of information. And then we'll talk about model-based classification and model-based clustering, which is a different approach. And I'll show you what mClust actually produces, and it's quite interesting in terms of how it actually stratifies your information. And then, as I was saying, you're trying to look for that new data, that nugget of information that you didn't see when you were looking at your data set. And that's why when I say, when you look at your data set, you're typically looking at it from if you have a small data set, it's fairly obvious to see some of the relationships. When you start getting to fairly large data sets, and when we talk about big data, that's when clustering kind of comes into place, because it's able to mine information that your eye wouldn't be able to catch. So that's something to think about. A problem with clustering is, the labels that it does produce may not mean anything. So it's a question of knowing your data and then making intelligent and understanding of that information that's being brought back. So as you're tweaking your methods to your clustering, that'll actually give you an indication if you're going in the right direction or in the wrong direction. It is not a science that is very direct, because you're kind of inferring based on the information that's being brought back based on your algorithms. And algorithms can be tweaked, and each one of them has a method of tweaking to provide more information or less information, and to delve into the information a little deeper. So clustering will tell you, which groups of examples are closely related, but it's up to you to apply the meaning. So yes, you'll see these groups, but then you need to dig deeper to understand what that inference is between the two groups and what the difference is between the two groups. And then you'll be able to understand, and that's basically understanding your data. So it's all about understanding the information that's being presented to you. Clustering by itself doesn't do that. So what we see here, and you'll see, I'm going to go through a presentation. I'm going to go slide into the code and run some sample code I put together to give you an understanding of all the algorithms and all the different clustering techniques that are available. So clustering techniques here from a data mining perspective. So what we see is, efficient data structures and functions for clustering. So within R, there are a slew of different functions that enable us to cluster. And I'll show you, there's a particular site, I actually have it within my slide here, is a link to a site, and that contains all the R packages that are available for clustering, and there are quite a few of them. So depending on what you're trying to do and what type of data you have, there are different packages available for each one of those particular scenarios. What we also try to make is, make your, the clustering reproducible. and programmable. And that's something we talk about when we talk about seeding your data. We want to make sure that whatever you write and you cluster, you're able to reproduce, because you're typically looking at random subsets of data, but you want to make sure that random subset of data is always the same. Otherwise, your results will always be different. And that's something that we, when you look at seeding, that it is quite important. Comprehensive clustering and machine learning libraries. So, as I've been working with R for quite a number of years, and in itself, from a big data perspective, what we're actually seeing is a path of approaches to handling large subsets of data. And the reason for that is, as most folks, if you used R, R uses everything that's in memory. So it typically will store everything in memory and then use whatever is in memory, and you'll actually run your algorithms against what's in memory. So, in the earlier days, you always had a maximum of, up to 2 gigs on either on your desktops or on some of the servers. Now we're seeing, up to terabytes of RAM to be able to store all this information and then be able to compute on it. So that's that's a sign of, a good trend for the folks that leverage R for statistics or for big data. So typically clustering, which just fits right in there, is being able to load these really large data sets and able to process them in a fairly good amount of time without having a very expensive compute system that needs to be behind the scenes. Integration with other analytic tools. We all know that R can, any data set you drive from R, you can export out and maybe leverage it with SAS, big data discovery, Oracle R. So there are a lot of softwares out there that can actually leverage the code that you write and let you enable further analysis downstream. So. Next. So data preparation. I think that's something that's sometimes folks don't get into too much, but it does impact the analysis that you would basically try to do. So 2 things that I say clustering as a whole doesn't do very well is all these missing data. It has a hard time handling that. And then the other thing is the variability in your data. So if you have, and this is what we call scaling, and you typically would want to scale all your variables to a certain degree to make sure that when you're actually doing a cluster, it makes sense. So if you had a variable that had, a 1 to 1 million and another one that had a 1 to 7, you want to scale those down to comparables. And it doesn't change the data. It just scales it down using logarithmic algorithms behind the scenes to make sure that whatever you're actually measuring is at the same scale and enables that, that plotting to occur at a much cleaner approach than if you didn't scale down your data. So that's, and you typically would see it in your graphs. And I'll show you some code that I've written which basically does some of this and explains what this scaling actually does. So when we go into clustering, there are 3 main approaches, and there are quite a few in between: hierarchical, partitioning, and model-based. So when we talk hierarchical, we're talking mainly an approach where you're looking at, let's call it a dendrogram, right? So you're looking at the closest points, and you're actually mapping the closest points and putting out this graph, and I'll go into a little more deeper in a couple seconds here. Partitioning, which is typically the Kmeans, and that's a distance algorithm, which looks at the closest items, does a measurement, and then leverages that to group items together. And then the model base is basically a Gaussian algorithm, which uses multiple models and actually brings all that together and plots all this information. The R function below, so this particular path here, if you actually go to this path, and I'll send this deck out anyways, we'll post it out on the site, it actually has all the different plotting algorithms and clustering algorithms available. And there are quite a few of them when you go to the site, and you'll be able to download them if you wanted to. But it actually goes through and shows you every, most of the algorithms that are currently out there. So if you're dealing with the CRAN site, they have some, but this one functions mostly on clustering. So definitely have a look, and it's a good read for the folks that are really interested in clustering. So we talk about clustering approaches. So the traditional approach is really, hierarchical or partitioning. That means you're using K-means or a heuristic approach to your clustering approach. So one is, like I say, based on distance. One isn't. One is more hierarchical, so very different, and we'll go through that. The other one is model-based, and there's one that's out there, the mClust. That's one of the major ones out there that actually does Gaussian approach to algorithms and to plotting. We'll go through that. Next. So we're talking about hierarchical approach. So when you're looking at this particular image, what you're basically looking at, is the distance between these two particular points, and then they basically join the next two particular points and the next two particular points, and they keep going until you have this particular hierarchical image of your cluster. So it gives you a different sense, and it's a different compute approach. Like I say, one is looking at closest distance, right? So it's looking at which two items are closer, and basically graphing out in such a way that makes sense in terms of when you're looking at it. These two items are closer, these two items, and it keeps building. So it's basically this recursive approach to building out a graph of what the data would look like. I'll show you some of that and how to highlight at the end when you finish graphing the clusters. Because typically what you'll see is a whole, this whole layer that could be quite overwhelming down here when you have a large data set. And it's quite hard sometimes to understand where the cluster starts, where the cluster ends. So we'll go over that. So some of the functions, so hclust or Agnes, or basically top-down, which is Diana. So one basically starts with everything grouped together and then breaks it apart based on distance, and the other one starts by everything is separate and actually builds everything up. So that's the two approaches. What you'll typically see is this one, the hclust, which is the bottom-up approach, is the typical approach. The divisive approach is really time-consuming, and you won't see a result that's sometimes quite fitting with your data. So it is very different in terms of the approach. So say the first one is typically the one that's used most often from an analytics perspective. When we go into partitioning, that's usually K-means, which is very standard in analytics. It's used quite often. It's fairly straightforward to use. Basically what you're specifying, and this is something, you're kind of playing around with this K cluster, right? So the algorithm requires the data set, but also what you're thinking of how many clusters you're going to have. Something that when you're doing a model-based approach, you're not providing that information. It's basically being given to you once it's doing its analysis. So that's something to think about. So when you're not sure, you'd probably use a model-based approach. When you kind of think you know what the number of clusters are, K-means is, quite a nice, it's quite robust in terms of its algorithms. It's been there quite a while and fairly easy to use. So basically, you're letting, the algorithm know how many clusters you're going to have, and it will assign the number of randomly assigned items to the particular cluster. And it's based on distance. So it's looking at the closest distance between all items and grouping those items together. And then repeats as the diagram below shows. As it starts out, you have particular groups, and it starts grouping into particular clusters until all the items are actually grouped into a cluster. So you typically would play around with the K. So you'd start, at a medium number, 3 or 4, either work down or work up, depending on what you're seeing in terms of graphing. So it is a very iterative approach to partitioning or clustering. So the function is really K-means. The similarity is K. It's basically how many clusters you're looking for, and then you work around those clusters and you try to figure out. You're basically trying to nail down how many clusters you're expecting. It is a different way of going about it, but it works well. And as I say, it's a very robust algorithm. It's been around for quite a while. Model-based. We're talking about M-Clus. M-Clus is, like I say, Gaussian. It actually leverages a number of algorithms behind it and looks at an average between those. And we'll go into each one of those. So you have really, when you look at M-Clus, you have your BIC, your classification, your uncertainty plot, and your density plots. It'll actually take your data and actually plot it out in those 4 categories, and you'll be able to see these 2-dimensional plots of your information. And as you understand your data, you'll kind of understand where your clusters kind of reside, and we'll kind of go through that. So as I was saying, M-Clus is typically the approach for model-based clustering. So let's talk about the data set I'm going to use. This is a clinical study that was done a few years ago based on Crohn's patients. It had about 118 patients in there. Each one had X number of adverse events. It was multi-centered, randomized, placebo-controlled, using 2 different drug regimens. One was an oral, one was an injectable. And I know what the clusters are going to be because I've seen the data, I've worked on the data, and when you cluster it, you don't expect what you see, and there are reasons for that based on the data that's actually injected, because we do look at it from an oral, injectable, and a placebo. Basically, you'd expect 3 clusters of information, but you don't. And we'll go into why that is later on. So your data set is basically events, basic sex, where the patients from, the treatment they were on, and there's some other variables in there. What I did do for this data set is actually convert a lot of the categorical values into numeric values to be able to cluster them a little easier. When you have categorical values, it kind of have to do a double pass on your clustering to be able to do that, and it is quite time consuming. So just for that, I kind of went the simple way. A little more information on the data set. This is the summary. So when we look at it, how many patients have to be decreased in terms of events, increased number of events, which basically stagnated, and then some of the patients had slight decreases based on their treatment. The breakdown in terms of country, breakdown in terms of sex, and the breakdown in terms of treatment. That's quite important as we look at when we look at the clustering algorithms. So in terms of loading libraries, so we have a couple of them, Caret, cluster, and mcluster. We'll go into each one, what each one of these do a little later on. The function Kmeans, what does that mean? It's a clustering algorithm meant for partitioning data. So it requires the analysis to perform a number of clusters and like I was saying, it's an iterative process. So you're basically putting a number in, and you're looking at what's coming back. And you're going to refine that number as you do your analysis. So just because you put in, like I say, a 3 in terms of number of clusters, that doesn't mean it's right. It kind of says, I'm going to start at a 3, and I'm going to work either a 2 or I'm going to work up. But it doesn't mean that 3 is right, right? So it's an iterative approach to looking at your data. Scaling, as I was talking about, so scaling lets you, let's say, calculate a mean and standard deviation of your vector. So basically, it's taking all your data points that you have in your data set and scaling them down to a particular value. And it doesn't change the data. It just scales it to where it's plottable. When you have values that are extremely high, like weight, you can have very high values compared to, let's just say, a number of events. Very different scale. So you're trying to make sure that that scale across your data points is evenly distributed. So your plots actually look more realistic. So seeding, as I was saying, seeding is really a way of providing the ability to reproduce your results. Otherwise, you would never be able to reproduce your result because you're actually taking a random sample of information and trying to, I say, typically what you would try to do is, do a test sample and then a full plot sample. So it's two different samples. What you want to do is make sure that when you seed is that every time you're doing your sample, you're getting that same sample back without hard coding a particular set of variables in there. That kind of makes your code reproducible. Otherwise, you just end up with a complete different graphic every time based on the subset of information it's actually using from your data set. And that's not too bad when you're using small data sets, but when you're using large data sets, it impacts it quite a bit more. Okay. So the Kmeans function, and I'll walk through this once I get into the code. Basically what you're seeing here is saying, all right, the first line is I'm going to cluster. I use 3, so I'm using my data sets as a Crohn's data set, and it actually breaks up the 3 clusters in 39, 36, and 42 subjects each. So, and when we looked at the distribution of the subjects that were on a certain regimen, we saw 39, 39, 39. So it kind of changes that a little bit. And once we get into the code, we'll examine that, and we'll look at the graphs, and we'll examine why that's happening. Then you have basically your clustering vectors, your sum of squares, and you'll see that sum of squares is 98%, which is quite good. Available components, and each one of these components we can go into individually. I won't look at that today because of the time constraints, but you can actually look at each one of these particular components and actually delve into each of them by looking at them. So it's quite interesting to look at. Plotting your data. So let's go right to the code now. I'm going to zip on out of here. Let's go into and clean up this. Clean everything out. So here are a couple of my packages that I've installed. They'll load up my libraries. Actually, let me clear the console here. That way you can see what we're doing. Load up my libraries. And put a 0 here because this is my M class kicking in. We don't want to do that now. I'm going to load up my data set. My Crohn's data set, so it's basically a CSV file. What we can see from the variables itself, so I converted everything into numerics, number of adverse events, BMI of the subject, height, country, sex, age, highlight, and treatment. Fairly straightforward data set, nothing too complex about it. I'm going to run a summary on it. So the summary gives us, basically, from our perspective, gives us some stats on each one of the variables that are in our data set. You know, with mins, the max, the medians. So that's also, you know, from a stats perspective, quite important to understand. You know, if you have like country, it says there's a max of 2 variables in here. Same thing for sex. If you have male or female, here it's U.S. or U.K. Age. We have 75 different varieties of age across the data set, right? And 3 different treatments that we know. So that's kind of information you kind of want to know about your data. So the more you look at this, afterwards when you're looking at your clusters, then you start understanding the clusters. So it's this combination of looking at your data, looking at your clusters, and refining how you're clustering. Second thing is scaling the information. As I was saying, it basically is a way of normalizing your data, and it actually goes through and looks at every variable and normalize it in such a way that when you're plotting it, you're not getting these scales that are that don't make sense. The table, and we'll take a look at this. And this is the interesting part. So you'll see that it says here I have really 3, we'll call it 3 clusters, each one out of 39 subjects. And that's because the treatments were all 39 subjects each. So when you're looking at this, and then you're looking at your number of clusters, right? There's a slight difference, and that's a little higher up here. And that's where you're trying to understand the difference between the two. Where I put it. And we'll get to it a little later on. I'll pull it up back up. So the next step is now that we've scaled. So heads and tails, I just put this in just for informational purposes. So heads will give you the first 6 records of your data set, and tails will give you the last 6. So it's so if you just want to look at your data, you know, it'll bring you up the first 6 records. This one will bring up the last 6 records. Quite interesting, just for informational reasons. No value from a algorithmic perspective here. It's just informational. So let me go right here and run my seeding. And you'll see here, I put in 3. And you'll kind of notice that 3 may not be the right number. So I'm going to run 3 clusters. Again, this is my data set, numerical number of clusters, running a K-means. So this is a partitioning algorithm. And then so it actually executed. So if I run the print, it'll bring out a couple things. So you'll see basically the 3 clusters, how they're broken out. And basically some of the stats on each one of the clusters, and the treatment here. So that's kind of interesting where you're seeing a very high number 2 and a low 3. So you get to look at the vectors. how that's built out. And basically some of, a sum of squares, also very important. And then your available components as we were discussing earlier on. So I'm going to run this, which is our table, classification. So it shows us this little matrix in terms of how the clusters are actually set up. So it's quite useful to know when you start looking at your data. So I'm going to plot this information. And what we're going to see is really three, and I set it to three. But when you start looking at your information, you're probably saying, all right, I can understand this one, and I can understand this one, but do I understand number two here? Number two seems to me like part of three. And that's where you start looking at, looking at your information. So well, maybe there are only two clusters in this domain, this data set, right? And this number kind of explains it right here. These two components explain 49% of the variability of your data set. So when you're looking at, and this is component one, component two. So this is basically going to PCA, which is principal component analysis. So the two major components equal 49% of your results. So if we actually did a two-clustered approach, and we can just change this to 2 and run our Kmeans and then just replot. We start seeing something that's more logical, and that makes more sense from a plotting or clustering perspective. And I have played with this from going from 2 clusters all the way to 7 clusters, and the 2 typically will be the best number in terms of understanding, the data set in itself. So, two aspects to that, and you'll notice there's a whole bunch of parameters to your clustering. You have your limiters, so your X limit and your Y limit, which gives you the X and Y graph. I typically use, and I said depending on the data, I will use and you can remove these. So if I actually said, I don't want to see this, I can actually take this out and regraph based on the 2 plots. And what you'll see is really and you'll see it basically goes from a 2 to a -3, and here a -4 to a -4. So the 4 was okay. The graphing of the 2 on the bottom axis, that's what changed. And I say, this is a small data set, so you typically won't see a wide variation, but on a large data set you would. So that's something to be cognizant of when you're actually plotting information. You have your colors and your labels. Labels, there are 5 different labels on this, depending on how much information you want to plot. It depends on the reports you need to produce, but typically how much information it could get quite busy. So 5 typically is a nice range, I think, for looking at information or analysis, doing your analysis. We go into how to fit. So here I have, I'm going to run this on 3, and I'm going to replot this. Okay. So this is another approach to plotting. Right? And you'll notice that the graph is slightly different, right? So when you're looking, I say, not all graphs are adapted to your data. So you kind of have to play around with your data, understand the data, and understand what you're trying to plot, because sometimes it just doesn't make sense. And you'll notice that, here we kind of see a whole bunch of different outliers, which we didn't see in terms of when we were plotting the first cluster plot here. And that's because of how this is actually getting plotted. So we're using a 3 plot here. So if we went back 3 cluster and we put 3 clusters in here, we would see a slightly different approach and we'll use the same label. So this has, I think, a label 2 on both of them. So you do see some outliers, but they're not grouped or clustered in the same cluster, so which is very interesting from a clustering perspective. So that's where you start delving into and understanding these particular outliers and where they stand in terms of your data. So that's always quite interesting. So that's fitting. Then you get into hierarchical clustering. As we were saying, so there are 2 approaches to that. And there's the average method, and then there's the Euclidean approach to distance. So it's a different way of measuring, and they do provide 2 different graphs. We'll go into that shortly. So let me actually run this one first, and it will plot this. So what we see, and say the height basically determines the distance between the 2. What you would expect from here, and as I was saying, it's pretty hard to understand where the clusters are. You would expect to see one cluster here, another cluster here, and then another one right around here. In terms of how that, the information is actually partitioned out. We'll run the other cluster, and I can show you. This is the Ward approach, which uses Euclidean distance measure, and it's slightly different. And pull this up. So you'll notice this is a very flatter graph. Although you do see 2 major, you kind of see more clusters involved in this one. I didn't get into too much of the details of why that is, but and it's really the distance measurement that it uses. One uses an average measurement, and the other one uses the Euclidean measurement. And that distance measurement is very different, and that's why you're actually seeing the number of clusters as they appear from a data perspective. So it's all based on that particular. So I'm going to try here is fit this into what we call fit the graph into 3 groups, and then plot these 3 groups, and then highlight the clusters. So what we will see here is really 3 different clusters. There they are. That enables at least to visualize where the clusters are, and then we can start delving into each one of these particular, and each one of these is pretty much a subject in that study, which we can actually just delve a little deeper into. So before I go into the MCLUST, I go back to my presentation and go down a little more in the information. So this one went through. So basically, as I was showing, this is actually your plots. This is a K-means plot. What I was explaining is that we see really 3, but there are actually really, when you look at the data itself, there's really two different clusters of information within that data set. and typically is because the distance between each one of these subjects is fairly nominal, and it partitions the data out, really, if you look at it, on two things. One is location of the subjects, and the other one is on the sex of the subject. And that's very interesting when you get into more of the details of the data itself. I've tried, I say, fitting it with 4 clusters, and you do see 4 clusters, but it really, when you look at it from a data perspective, it doesn't make sense. And I've tried with 5 and 6 and 7. So as you play around with your data, you kind of look at your data, you understand your data, and then you try to plot that data and understand what that meaning means from a clustering perspective, what those groupings mean. So as I was discussing, so clustering from a hierarchical perspective is this linkage between the items. So what you're trying to do is link each item using a default, I say, measurement, right? The K-means uses distance. This is using basically a measurement between each one of these, and it's actually grouping everything together, and you end up with this particular approach to where it's the clustering minus all the errors. And that's what gives you your graphs. So it's a slightly different approach to groups, but it does make sense for certain aspects of your data. So you end up with these kind of graphs, which are hierarchical graphs. I say the higher, the closer they are, the closer the items are. So they get fairly close down by and get further apart at the top. Ward, slightly different. You know, the height changes, and you kind of see more of that relationship kind of in terms of distance kind of is removed, and everything gets a little closer. That's where you would want to separate out these particular clusters. And this is how I do it. Highlighting these particular clusters, and you can say highlight 4, 5, 6, and it will actually split the data up in particular clusters to understand the information a little closer. So model-based clustering, always quite complex, and it does take a while to understand each one of the graphs, and we'll go through that. And each one is fairly, I say it's a 2-dimensional graph, but looking at each one of the components. So it kind of builds out these really, really nice approaches to understanding your information, your data. So what is it comprised of? So it really is when we're talking about, MCOS, it's looking at these 4 different approaches. One is your Bayesian information criteria, your classification, your uncertainty graph, and your density graph, all of which can get generated from your MCOS. And each one of them gives a different explanation to your information or your data. And each one provides a little more information in terms of what the relationships are between the items in your data set. So your BIC is basically, and you're looking at this, is basically a relationship approach to your items, and each one of these is a variable in your data set. So what we're seeing here is, I think, the severity one is from an explanation point, I'd have to go into a little more into the data to explain what that means, but we'll look at it from actually the code itself. I think it'll make much more sense. The model-based classification, as I was saying, each one of the variables, and it's basically comparing 2 of the variables at the same time and graphing those out. So the more you look at the information, then you can start seeing where your clusters are from your data, and it infers the number of clusters. So you're basically not providing the clusters to like K-means, where you say I want 3 graphs, or wards, I want 3 clusters or 3 clusters in K-means. You don't do that. You're basically letting the code do the clustering for you and determine how many clusters you're going to have. Uncertainty graph, which is basically the opposite of the classification, and then the density one. And that's where you're looking at two different attribute components. Right? And I'm going to go into the code right now, and we're going to go through that. So here's our mclust. I'll run that. I'll fix that. All right, so what you see at the bottom is a prompt. So it's basically asking you which graph or plot do you want to run. So let's run the first one, the BIC. So what we see here is basically a deviation between the two. And we're basically looking at really two clusters when you look at this. So you actually have 1 and 2. As we're explaining the K-means, I said, well, there are three. I put 3 clusters in, but they're actually just 2. And this basically, and this is actually looking at it and saying there's only 2 clusters here. And that's the reasoning behind that. There's no more than that from the explanation of the data. Next one is the classification one. Also quite interesting. So when you run it, you do get a 2-dimensional plot, but you're looking at each one of your variables, and that's being plotted. So weight and treatment right here, and then you're actually going at age against weight, age against treatment. So basically that's what it's actually just plotting each of the variables against each other, and you're actually looking at the center points right here and where the clusters are within your data. It does take a while to sift through all this information, but it is quite useful when you try to understand where those variations are in your data and understanding the graphing of it. The uncertainty one. So, and this one is a little more complex in terms of what it's actually producing. It's giving you, and you'll see between the 2 clusters or 3 clusters, how much uncertainty. And when we're talking about uncertainty, it's that distance that's being calculated out, how accurate it is. So we can spend a lot of time on this, explaining what we're looking at, but yeah, it's basically doing the same thing as the classification, but it's looking at the opposite of that. And the last but not least is your density graph, and that's always an interesting one. Oops, wrong one. So what we're seeing here, you're looking at correlations of, and this is all based on PCA, right, principal component analysis, and you're comparing 2 items together and saying, okay, what the correlation is between the 2 and how closely they're related. And this graph is quite interesting when you start looking at the darker sides, because that's really where the important stuff is. Where it's very light, those are the ones you probably, there's not much variability in those, so that's quite important to look at. And then you can delve into those particular data points which you think are of value when you're looking at these particular plots. All right. All right. That is it for the presentation. I can take some questions. All right then. want to thank everyone for attending. Have a good night.